Now that we've taken a look at some very basic setups for bases that are orthogonal, magnitude 1, we call them orthonormal bases. What do we do if we have a basis and the vectors are not of magnitude 1 and they're not perpendicular to each other? That's the hard part. We need a process called the Gram-Schmidt orthonormalization process. So I wrote the process out in a sheet of paper. Here it is. Take a look at it, and then we'll go through a couple of examples. We start off with a basis, right? Basis of v vectors for some inner product space. So you already know that it's a basis, that it covers everything it needs to. Here it is. I'd like to transition to a different basis where the vectors are perpendicular. So let's hold that first vector as it is. So the W1 will be the same thing as V1. And this second vector, W2, will be V2 minus the inner product space of V2 W1 over W, W1 times W1. In other words, the projection of this vector on the other. So there's my coefficient times W1. Now, for the third vector, it gets a little more complicated because now you've got to subtract the projection on W1 and the projection on W2. When you come up with those vectors, you've got an orthogonal basis. Now you need to go one step further, that's step 3, and develop an orthonormal basis. So your first goal is to come up with an orthogonal basis by subtracting off those projections. When you get done, then you need to normalize all those vectors until you have an orthonormal basis. So let's take a look at an example, 2 examples, 3 examples. Let's see how far we go and how long this takes. So here is our first example to do some Gram-Schmidt. Gram-Schmidt. Let's say I've got this basis here, and it is 3, 0, 4, negative 1, 0, 7, 2, 9, 11. And this is a basis for R3. So anything in R3 can be written as a linear combination of those 3 vectors. I want to find an orthonormal basis. Now, it's never hurts to check. You might luck out and take a dot product of the 2 vectors and come up with a 0, but you don't. In the first case, you come up with negative 3 plus 28, which is 25. In the second case, you get negative 2 plus 77, so clearly not an orthonormal basis. The first and last don't work out either, I don't think, right? 3 times 2 is 6. 0, 44, no. 44 and 6 is not 0. So we're going to need to first create perpendicular vectors. So first, orthogonal vectors. Then orthonormal vectors. So W1, that's in my new basis, will be 3, 0, 4. Now, it's up to you how you want to organize this. In other words, you can create orthonormal vectors right away, or you can create the 3 perpendicular vectors and then find their length. If you find out that you keep forgetting to take the magnitude, then you might want to do the magnitude as you create the vector. I'm going to do them all at the end because I'd rather do it that way. All right, the second vector in the now orthogonal basis will be V2, which is negative 107 minus the projection. So V2 is negative 107 minus what? Go back to that formula that I wrote down or that you wrote down, is going to be V2W1. So V2 is negative 107 dot W1, which is 304, over the dot product of W1 and itself. So 304 dot 304. That's the coefficient that gets multiplied by the vector 304. All right, take a look at the dot product up on the top. Negative 1 times 3 plus 4 times 7. Well, 4 times 7 is 28. Minus 3 is 25. Down the bottom, I get 9 plus 16. Oh, 9 plus 16 is also 25. 25 over 25 is 1. So really, W2 is just negative 107 minus 1 times 304. So that gives me negative 1 minus 3 is negative 4. 0 minus 0 is 0, and 7 minus 4 is 3. So there is W2. Now, of course, W3 gets a little bit messier. W3, I'll try to start all the way on the side and see if I can fit this across. W3 is going to be V3. What was V3? It was 2, 9, 11. Minus V3.W1. So I get 2, 9, 11 dot W1, which was 304. I already know what W1 is. It's 25. I already did it in the previous step, so I'm not going to write the whole thing out. So that times W1, which is 304, and then minus V3W2. Well, V3 is 2, 9, 11. W2 is right there, negative 403. Now, you realize why this can be a pain sometimes, because if your W2 is wrong, your W3 is going to be wrong also. And then down the bottom, you've just got negative 403 dot itself. And the vector you're multiplying by there is negative 403. So you realize whatever vector you're working with, you're going to have a lot of them in the problem. All right, so here we got 2, 9, 11. What's the dot product up on top? 2 times 3 is 6, plus 0 plus 44. Oh, that's 50. Take 50, divide it by 25, I get 2. So minus 2 times 304. And now, what's this mess up on top over here? 2 times negative 4 is negative 6, plus 0 plus 33. Did I just say 2 times 4 is 6? Where have I been? 2 times negative 4 is negative 8. And then 33 minus 8 is 25. Down the bottom, I'm going to get 16 plus 9, which is also 25. So 25 over 25 is just 1. So minus 1 times negative 403. Now take the components very carefully and add them together. So W3 will be 2, maybe it's worth doing it on the side over here, 2 minus 6, minus a minus makes a plus 4. So 4 plus 2 is 6, minus 6 is 0. Interesting. The second one is going to be 9 minus 0, which is 9. And the third one is going to be 11 minus 8 minus 3. Turns out to also be 0. So my third vector goes only in the j direction. All right, next step now is normalize. So the first vector, W1, was 304. Every once in a while, you'll find one that's already of magnitude 1. Not going to be so in this case. The length of W1 is the square root of a squared plus b squared. So a squared is 9, b squared is 16, square root of 25 is 5. W2 we found to be negative 403. So the magnitude of W2 is going to actually be the same thing, because negative 4 squared is 16. That's 9. We'll get the square root of 25, which is 5. And W3 is easy, right? If it's 0, 9, 0, the magnitude of W3 is the square root of 81, which is 9. Now find the unit vectors. So the unit vectors are these vectors here divided by their magnitude. First of all, if you look through these three vectors, can you see that very least they're orthogonal to each other? 3 times negative 4 is negative 12, plus 12 is 0. If you do the second and the third, you get 0 plus 0 plus 0. Do the first and last, you get 0 plus 0 plus 0. All right, so the first unit vector is going to be 3 over 5, 0, 4 over 5. The second unit vector is going to be negative 4 over 5, 0, 3 over 5. And the third unit vector is going to be 0, 1, 0. So if you want to write my new basis nice and fancy with the set notation, it'll look like this. 3/5, 0, 4/5. That's nothing more than the original first vector we were given, except written in terms of a unit vector. -4/5, 0, 3/5. And the last one is just actually j. There's my answer. You can verify that they're all perpendicular and that they're all of magnitude 1, and that is my orthonormal basis in R3. So what do you think? You want to try another one? What if I put this one up, you pause this and work this out, and then come back and we'll see if we all get the same answer. So here's my next example question. Okay, let's see if you want to give this a try. Pause it, and then see if we come up with the same answer. So here's my basis. I'll try to make the numbers relatively small. So my basis has vectors 1, 1, 1, 0, 1, 1, and 0, 0, 1. Well, that third vector is already a unit vector. The other two are not. Are any of these vectors orthogonal to each other? No, the first two are not. Second two are not now. So these vectors are already not perpendicular to each other. My goal, I want to create an orthonormal basis. All right, you do it. Come back and let's see if we match. All right, so here's my process. My W1 is going to be the same as the original vector that's up there, 1, 1, 1. All right, I'm going to start from the left and work through. My second one then will be V2, right? I'm calling this V1, V2, V3. So the second one then will be 0, 1, 1 minus V2W1. So 0, 1, 1 dot 1, 1, 1 over 1, 1, 1 dot 1, 1, 1. Am I really going to write this? Yes. Times 1, 1, 1. All right. On the top, 0 times 1 is 0. 1 times 1 is 1. 1 times 1 is 1. So I get a 2 up on the top. Down the bottom, I get a 1 plus 1 plus 1, which is 3. All right, so 0 minus 2/3 is negative 2/3. 1 minus 2/3 is a third. 1 minus 2/3 is a third. I'm claiming that that vector is W2. All right, let's go up and find W3. W3 is going to be 0, 1, 1 minus V3W1, so 0, 0, 1 dot 1, 1, 1 over 1, 1, 1 dot 1, 1, 1, but I already know what the answer is. It's that number right there. It's a 3. That times W1, which was what? 1, 1, 1. And now we're going to do another subtraction of V3W2. So 0, 0, 1 dot that vector that I just came up with up here. Negative 2/3, 1/3, 1/3 over that vector times itself. So negative 2/3, 1/3, 1/3 dot negative 2/3, 1/3, 1/3. So it's going to be that times that vector W2. All right, so there's some fractions involved, but I think they'll work out nicely. All right, let's try this. W3 is going to be 0, 1, 1 minus 0 times 0 is just 0 plus 1. So I get a third times 1, 1, 1. All right, that comes out to be 1. So a third times 1, 1, 1 is a third, a third, a third, minus. All right, let's see what we got up here. Not bad. 0, 0, 1 times a third is a third. On the bottom, I get 4 over 9 plus 1 over 9 plus 1 over 9, so 6 over 9. 6 over 9 is 2/3. So this fraction up here is 1/3 divided by 2/3. It's just a half. Times negative 2/3, 1/3, 1/3. All right. And when you've come this far, it's always good to spot a mistake before you get all the way through to the end. And now that I'm looking at this, I realize this thing should be 0, 0, 1. So that should be a 0. And that guy over there should be a 0, which is good that I haven't finished this all the way through yet. Let's combine these first two and then the last one. So the first two combine to be negative 1/3, negative 1/3, and then 1 minus a third is 2/3. Let's do plus, and I'll distribute the negative sign. So that will give me a positive 1/3. It'll give me a negative 1/6 and another negative 1/6. All right, combine them together. So negative 1/3 plus 1/3 is 0. Negative 1/3 minus 1/6, so that's negative 2/6 minus 1/6, negative 3/6, or negative 1/2. And now the third one is going to be 4/6 minus 1/6, which is 3/6. That's positive 1/2. And that's your W3. Now we want to find magnitudes and create an orthonormal basis. So let's hope I wrote this down somewhere because this is scrolled way up. My W1 was what was originally given to me, which was 1, 1, 1. My W2 was negative 2/3, 1/3, 1/3. And my W3 is sitting just on the top out of sight. It's 0, negative 1/2, 1/2. I can see here that the magnitude of this vector is going to be the square root of 1 squared plus 1 squared plus 1 squared, or the square root of 3. So my first unit vector will be 1 over root 3, 1 over root 3, 1 over root 3. All right, this guy over here is going to be the square root of, now square everything, top and bottom. 2 squared is 4, so I get 4 over 9 plus 1 over 9 plus 1 over 9 gives me the square root of 6 over 9, which is square root of 6 over 3. So I should take W2 and divide it by square root of 6 over 3. Well, dividing by square root of 6 over the 3 is the same thing as multiplying by 3 over the square root of 6. So let's do that. Let's multiply by 3 over the square root of 6 of negative 2/3, 1/3, 1/3. And you see that this works out nicely, that the 3's top and bottom cancel, and you end up with negative 2 over the square root of 6, 1 over the square root of 6, 1 over the square root of 6. All right, there's U2. All right, U3. Here I'm going to end up with the square root of 1 over 4 plus 1 over 4, which is the square root of 1/2, 1 over root 2. So instead of dividing by this, let's multiply by the square root of 2. So U3 is going to be 0, negative square root of 2 over 2, square root of 2 over 2. So again, rather than divide by 1 over the square root of 2, I'm going to multiply by the reciprocal, which is square root of 2. All right, let's take these three vectors, line them up, and see if it makes sense as an orthonormal basis. Okay, my basis then is 1 over root 3, 1 over root 3, 1 over root 3. That's the first vector. Second vector is negative 2 over root 6, 1 over root 6, 1 over root 6. And the third vector is 0, negative root 2 over 2, root 2 over 2. How do I know I'm right? Well, each of these should be of magnitude 1. I can go through quickly and compare, right? The first one's going to be a third, a third, a third. This is going to give me 2, 6, 1, 6, 1, 6. Add them together and take the square root. That should all, well, 4 over 6. 1 over 6, 1 over 6 adds up to 6 over 6. And the last one should work also. Then if you want to find out if they're perpendicular, take the dot products. All right, so take the dot products of each of those vectors, and you should get 0. Therefore, I have created an orthonormal basis. And that's the end of Gram-Schmidt.